Hi everybody, welcome to today's workshop, Generative AI and to create image and deepfake videos. So I'm your presenter today. Okay, so let's get started. Before we started, allow me to do a brief introduction about myself. Right, my name is Sun Yao Cheong, or you can call me Sun Cheong. So I'm an entrepreneur and I am basically now a consultant in AI. So I help businesses to devise AI strategy, to do some research and R&D, and also to implement these kind of solution and in deployment. So some of my past existing and past clients including Samsung, etc. And I also work for many big companies like Nvidia, Qualcomm, etc. So you are welcome to connect with me on LinkedIn. Right. So I now just talk about me and about this generative AI. So I started playing with GAN, use AI to generate stuff since 2018. So there is a link of a video to the video that I created a few years back to show one of my earlier work in trying to use generative AI to generate fashion design. So if you have time, feel free to take a look. But the quality was no the outcome is not that great because limited by the technology at the time. All right. Okay, so we will get started now. Okay, I think I can turn off the camera now. Let's just focus on these slides and these guy and the code. Right. Capture. Right, there we go. Oh right, forgot to mention I am also a book author. Um, of these the book called Image Generation with TensorFlow, which was released in half a year ago in end of December 2020. So I guess that's the reason why the conference organizer found me and invited me to give a talk on this to deliver a workshop on this topic. And okay, so this is a tweet from this creator of Keras, Francois Charlotte. So he obviously liked my book and just thought I wanted to share with you guys. And he did especially mention about the style gun. So style gun is a state of the art model to generate faces. I believe this is currently the only book that details how to create style gun from scratch. So if you are interested in this kind of topic, create a really good high quality images, you should probably check out this book. All right, so this is the question I get asked a lot, right? If somebody wanted to start playing with computer vision or generative to generate image video, so which machine learning framework to use. So there are pros and cons, and there are a lot of debates on which one is better. But from the my view on using them to generate images. So these are my conclusion. So PyTorch is probably a bit better for research. It has it's more flexible in creating your architecture, your custom model. It is more flexible in that way. But on the other hand, it is a bit low level. That means you have to have good knowledge on the underlying network layer. Say for example, if you were to use convolution layer, you have to know that which padding to add to the input to create the output size that you want. But so if you know about that, then if you're a researcher, then it's no problem to you. But if you do not want to get into those more details, then these TensorFlow 2 Keras API is probably easier for you to learn. So I think from education perspective, TensorFlow Keras is probably a slightly better choose for like people to get started learning about the principles of like generative model. But to me, it doesn't really matter. All these like modern machine learning framework, they are quite similar. If you know one framework, it's quite easy to understand the other and port it to the other framework, so it's fine. And in this tutorial, so in this workshop, so I will use TensorFlow code, but as I mentioned, it's quite easy to understand even if you come from if you are primarily use PyTorch or other machine learning frameworks. Right. So and just one final note to add about TensorFlow. So TensorFlow, there are two versions. One is TensorFlow 1, then the latest one is called TensorFlow 2. So TensorFlow, some of the old GitHub repo that you can find use TensorFlow 1. So there is a bit difficult in my view. Most of people think that TensorFlow 1 is quite difficult to use, but TensorFlow 2 is because it incorporates the Keras API as the main API, so it is a lot easier to use. And we shall see, we can actually create a model with just a few lines of code. Right. So about this one, this should be chapter 1. So what we will cover is like I will briefly talk through about the use of probability, what that means in the context of generative AI. So this is comes from the chapter 1, okay, from the book. The reason for me to include in this workshop is that most online tutorials that you can find, they focus on teaching you how to code, how to write the code, how to write PyTorch or TensorFlow code to create the model, but without explaining why you need to do things in certain way. So that's why to most people, like this deep neural network is a black box. And I think having some understanding of what probability means will help you to appreciate these or appreciate and understand deep learning a lot better. And then in this, then we'll move on to introduce and actually implement this autoencoder, which is a type of neural network that is quite simple, but it's very powerful, and we will use that to run some experiment in how do you use that to generate not only generate, but also you can use that to edit your face. Okay, finally, this deepfake algorithm is we use that to create deepfake. Okay, so I believe most of you should have know what deepfake is, but if you haven't, you can go on to YouTube to find a deepfake video. So I found one and I can show you. Alright, so what it really means, what it is. So this is a YouTube that I found. Somebody used this deepfake to swap the face of Iron Man with Tom Cruise. Okay, let's play a little bit.
Nations and corporations the world over will pool their resources, share their collective vision to leave behind a It's not about us. Therefore, what I'm saying, if I am saying anything, it's work with that.
Right. What is the crazy one? Pretty simple. We draw them and put them down.
Definitely not my case.
Alright, I think that's enough. Okay. So I think you guys can agree it is pretty convincing. Not only you can use what they call it, swap the face of the Iron Man with Tom Cruise, and also it uses kind of also deepfake the voice. I'm not sure whether he created the generate the voice or he just asked somebody to voice over. Not sure about that. Okay, so those is the sophisticated technology to create some very realistic result. So, but due to the limited time of this workshop, so I will be introducing the very first original deepfake algorithm, um, where you can run the code and try it for yourself. Then finally, I will give a brief introduction to GANs, Generative Adversarial Networks. This is the most talked about neural network. So many of these amazing results that you see online, they are actually generated using GAN. But also increasingly, people also start to use a variant of autoencoder to generate images. So I think these are the two important models that you should learn if you are into this field. Okay, so I'll give a brief introduction to so it's my definition of machine learning. So many people have a different interpretation of what machine learning is. So in the context of for what I think is that the machine learning is to you create a model or an algorithm to learn the probability distribution of your data. It is this is what it is all about. So the more common type of machine learning is what we call a discriminative. It is, for example, you create an image classifier to try to classify the image into whether it's a cat or this dog. So two classes. So you discriminate whether it's one class or the other class. And the other one is, of course, is generative. So after you learn about your data, use your model to learn about your input data, then you can speed up. So you can generate new data, new kind of data. For example, you can generate image, so which will be the focus of this workshop, or you can use it to generate text and music, etc. So text will fall into the domain of NLP, natural language processing. So although different generative different what you call different if you use NLP or computer vision image, the model is different, but the underlying principle is the basic principle is the same. That is to learn the probability distribution and then recreate that. Okay, so I'll give you an example. Say, I'm sure say you have or you have tried to do a Google search. When you type in something, so you type in a few words, that it will give you some suggestion. So in this case, so we have three words: I want to. That's fill in the blank. What is this one? So what happened is that the algorithm will try to look at all the words, or in this case, all the phrases, to list out what has the highest probability that you will want to say that. So in this case, say eat maybe 10%, more like linear probability. Maybe watch TV 10%, do nothing 10%, or be rich 65%, and then the other I just group everything others as 5%. So there are the many. So the language model will try to build a probabilistic model, and then when you prompt it to put in I want to, it will just calculate so what is the most likely, and then it will give you the one with the highest probability. Alright, so then now let's talk about image. So what does this probability mean in image? Okay, there are two pictures here. So on the left is a red apple, and the right is just random noise. So what do they have in common? they actually have the same probability distribution. In other words, the picture here on the right, random noise, looks like random noise, have the same amount of red pixel and same amount of like green pixel. So I created this one by resampling the pixel. I just like reshuffle and then put them here. So this kind of show you the challenge in learning the distribution of images. Okay, so one of them is that it is not enough to say it have the same amount of red pixel, but they have to be in the right position, right? Be in the right position so that you can form a shape to consider what we understand as an apple, right? So you cannot have a bit of leaf, like say. So it have to be one lump of like green of red shapes for us to understand this as an apple. That is the one of the challenge. So you cannot just randomly we cannot just look at the individual picture and then calculate the probability, because it doesn't make sense. It just doesn't make sense, right? So next is that we will go briefly to introduce about the pixel. So we all know about pixel. We all heard about pixel, right? How megapixel is your camera, etc. So it is the smallest element of your any digital image. So the smallest dot. So if you look at if you open up a image file, if you keep zooming in, then you will see a square box. So these are pixelized. So these are one pixel. So one pixel consists of 3 color channels. So one pixel is like have red, green, and blue. So what we see, so with this, the mixture of these 3 different colors, these 3 primary colors, we can make a different type of power, different type of like all kind of colors and different shades. And each of these channels is represented by 8-bit integer. So it can form 256 different values. So if we so then how many possibility is, or how many different type of color can a pixel have? So we can just put that into this calculation. 256 times 256 times 256 is like 60 million. Okay, 60 million for one pixel only. You can have 60 million different type of colors. Although some of them is like we human eye, we cannot distinguish between some of the colors. But in theory, there's 16 million possibilities, all for one pixel. So what about like we have a 1 megapixel image? So 1 megapixel is actually relatively small in today's standard. But if we were to build a probability model to try to learn that many, I don't know how many million or trillion, billion possibility, it is just simply not feasible. That is why we will use neural network to help us to learn these distribution. If we go back to the slide before, so although we can say that each pixel can have many different possibility, but it is not true, because that, let's say if we look at this pixel here, if we know that this is a red, okay, then the pixel next to it is also likely to be red. So that removes a lot of other possibilities. So this is something we can take advantage of when this is something we can take advantage of to help to reduce this kind of possibility in different type of. So when we want to say generate a new pixel, so what pixel should we generate next to this one? Then we can reduce the range of things to try. Okay, so but this is still a very, very difficult task because there are so many pixels. That's why we employ this deep learning or deep neural network to help us to do that. So in this workshop, I will use deep learning, machine learning, neural network interchangeably. They basically mean the same thing. All right. So now we can get to look at some codes to generate our very first image. Oh yes, we haven't learned any algorithm, but you don't actually need any algorithm to generate image. All you need to have is a data set that we can use. So this is the GitHub repo of the book. So I will use the example from this repo, and this is a short one. If you just want to lazy, so this long. So if you want to type into your web browser now, you can use this, but it's only for temporary, so it will expire after a few weeks. And one note, so the TensorFlow version that I use is 2.3.1. You can use 2.2.0, but never 2.4 or above. Is not compatible because the API change, so it's not compatible anymore. Okay, right. So let's go to this repo. And by the way, if you have local machine that you can just git clone and run with GPU, then you can do that. Otherwise, you can also use Google Colab. So in this case, I will use Google Colab to do the demonstration. So now click on this one and go to the link. Right, so this is the GitHub repo. I will just quickly go through the page, the README page, and I wanted to show you something. Okay, so this is, if you can see, this GIF that I created using the code in the book. This is a style gun to generate faces. So all these two faces, they are fake. They're just created out of thin air. And then what it is doing now is then it try to change some of the parameter so that this one looks more like the man here. Okay, right. If you right, and I can also change the pose, the head pose from this one to get the head pose from this woman, and then to apply that on this man. We can just look at it for a while to see how it change. Yes, right. So it become, the face feature is become more like man, and you can see obviously the hair become shorter as we kind of copy the style of this man into the woman. All right, and the last step is to change the whole head pose. All right, okay, that's it. So okay, so this is style gun, but what we are going to it's not what we use today. So the best way to upload the code to Colab is to actually fork the GitHub repo to your own GitHub. So you can just press fork, then it will fork it into your. So I've already done that, so I didn't have to do it again. Of course, you can also upload your git clone to your local machine and then upload it to GitHub, to Google Colab. So now let's go to Google Colab. So I will just shut around this way. Google Colab. Alright. Right, as you can see, there are a few options. So one, I will say Google GitHub. So this is, well, you can enter your GitHub URL. In that case, I will just use my ID. Then it will search all the GitHub repo that I have. So I pick this one. Right, then it will list all the notebook available. So I will run the first one. So in chapter 1, ch1 generate first image. Okay. All right. Just to show how we can use this one. if you haven't used like Google Colab before. In this example, we do not need to use a GPU, so I will just leave it as a default CPU, so we don't do anything. So to run the cell, I can either click this play button, or we can press Shift Enter. Okay, it will just give you a warning. Okay, ignore that. Alright. So in this tutorial, actually, all the tutorial today, we will use the Select A dataset. It's a very famous dataset that consists of many faces of celebrities. So luckily, so this is included as TensorFlow dataset. You can just pip install TensorFlow dataset if you're on usual local machines. You have to install that. So if you go back to the GitHub repo, so all the requirements are in this file. You can just do a pip install to install them. Right, so you will get this. You are very likely to get this error. That is because I believe it is this dataset is so popular that many people try to download it. So it caused some like network traffic problem, something like that. So it always can return these error, but it's okay because I have then uploaded these dataset to Google Drive that you can download. So all you have to do is to comment this out and then hit run. So where there's no OS. Okay, OS. All right. So while we are waiting, I will just keep try to explain the what we want to do. So in this case, as we can see, no, so the image are gone now. So the image have say the celebrity faces, and each of these image have some label annotation of these facial attributes, such as whether you have beard or not, woman or man or woman, or whether they're smiling or not smiling, and then you have blonde hair or not. So it is a binary class. So not it's just classes whether you have this attribute or not. So they can have a combination of different attributes on one image. So this is something we can exploit later to help us to generate the faces that we want. So these are some of the examples that we can see. Right. So the next step is, okay, can I, right. The next step is what we want to do now is that we want to learn about the distribution of this data set and then use that to generate our first image. So what we actually will do is ridiculously simple. That is to simply take the average of every single pixel, of the pixel. So what I mean is that, so if that the top corner, there's one pixel here. So I collected the pixel, the top left corner pixel of every images, and then I calculate the average. All right. Oh, it's that simple. So what I do now is instead of taking the whole data set, I just take like 20 image, 2,000 images to reduce this time, the computational time. And by the way, the convention we use in this network, in all the code is that the shape of the data is in NHWC. N stands for the batch size, and H is the height of the image, W is the width, and C is the channel, which is always 3 for color image. Right, so this is what we got. I just run it again. this is our mean phase. Okay, means stand for like average, so we use mean phase. So this mean is calculates all the the pixel on this axis 0. That means it, as I said, it just calculates the average of all these pixels on the same location. So this is what you get, a mean phase. So we can see that, oh, it's quite to me it was like quite amazing when I saw it the first time. So I didn't have to do anything, and I can create an image like this without any like algorithm really. So it is a smiling woman with a smiley face. So we can see that the background is a bit is a blur because, well, by when we take average, it has this blurring effect. It can remove some of the noise. And why? Oh, just some added bonus is that why is there the background gray in color? So we can see we have a variety of different colors. The view is that, so this called, I think it's called, there's a term called, I think, gray world view in this computer vision literature. That means if you take the average of all the color in the natural world, it tend to be gray. So that's why you average all the blue, green, everything together, it just become a gray color. All right, and let's see. Okay. Then what we will do next is that, okay, it is not quite efficient to only be able to generate one phase out, so like 2,000 phases. But if you wanted to generate more, or what if you want to generate phase with different attributes? So that is also another very simple thing that we can do, is that we can make use of these phase attributes. Instead of we taking average of every single image, we only pick the images that with certain attributes that we want, and we take an average of that. So this is what we do. Let's see. All right, I think I'm not going through trying to explain each of the line. I'm just going to give a high level walkthrough. So these are all the different attributes. As you can see, some are more common than the others. For example, you're saying there's a male or not male. Of course, you have to be either category male or not male. Okay, but by the way, what I was thinking is purely from this data set. There's not there, of course, they are in reality they are non-binary, but in data set are male or not male. Okay, right. So, all right. So in this cell, this code, okay, I think I probably should move this one into a middle a bit. Sorry, right. Try to make it bigger. Right. Okay. So what this code will do if you run it is that it will go through each of the item in this list. So in this case, for male, when it is set to true, it will read it will collect the images with this attribute set to true, and then we take an average. Then there's a loop. It basically just keep adding the one attribute to the one previous, and this one add to male and eyeglasses, etc. And this is the result that we can see, right? So if we only say, so it's the same data set, but well, in this case, I think I took the entire data set rather than just 2,000. So this one, there are about 7,000 images. So with this male set to true, so this is the average phase. So this is something that can be quite useful. Say for example, you have some many images of your data has some images, and you wanted to know what the average that people looks like. You can do something like this, just average out the pixel to give you some idea. Okay, so this is male. This one is male with eyeglasses, as you can see. Well, we just literally just added eyeglasses onto this one, and then eyeglasses with a mustache. So in this case, in this one, we can see that the sample size is actually a lot fewer than the previous one. That's why it's also tend to be more noisy, because there are not that many images that match all these criteria. And finally, we have this one, all these things with smiling equal to true. We can see that, oh, this guy is smiling now, but we of course can see it is a bit noisy in the background. Right, mean is not the there's a using mean is a very simple way, but there are also other things we can use. We can use median. So median tend to give a sharper images, but be a bit more noisy. So I repeat these experiments using different attributes and replace the numpy.mean with numpy.median. By the way, NP is numpy, is a very common Python library that we use to process numeric numbers, numeric data, especially for but we use that a lot with a machine learning framework like PyTorch, TensorFlow. Right, so just show you example. So when male is false, so this is what we look like. This is using median. Okay, with eyeglasses, etc. Without smiling, and this is no smiling. Still no smiling with pointy nose. Alright, so this one is what we can do without any model, without any algorithm or machine learning framework. Okay, so next, so it is actually, if you can see, so the quality is a lot crude compared to what is actually possible by using deep learning to do. So the next we will learn how to use deep neural network to create image properly, do it in a proper way. Okay. Right. Right, slideshow. Okay. So I assume most of you have some basic understanding of or hands-on experience in creating or using a neural network. So I will just go through this slide very quickly. So in general, what we will need is your input. So in this case, is image as an input to our neural network, and the target. So if you use image classification, so the target is your label. So what the class label, and then the model or algorithm, or we just call it neural network. So this is what we will create, and then the loss function. Loss function basically it compute the error between your prediction, the output of your model with your target. And if it is close to perfection, then you get a zero error, zero loss. Or on the other hand, if you get a very big loss, then it means your model is not good enough. Then we will use this optimizer to try to teach the model to make a better prediction. So these are some of these common optimizer. There are many more, but I'm just going to give a brief introduction to some of the more commonly used ones. So SGD is the vanilla, so stochastic gradient descent. Don't use it, it's slow. So by default you should use Adam. So Adam is fast, and despite sometimes it doesn't quite reach the optical the best result, the global minimum. But unless you are trying to to win some machine learning competition. You try to make the best, improve your accuracy by 0.0001%. Then you might need to use something different, but that for us, Adam is good enough. And there's another one. It's called RMS prop. It is quite similar to Adam. I think this is only mainly used by Google, because this is the invention of Jeff Hinton, the godfather of deep learning, one of the godfather of deep learning. I think who is now employed by Google. So many of the work of his students use RMS prop. So in my book, I use either RMS prop or Adam. Right. We will only create some. We won't be to do something like style gun. There are many techniques involved. So it's not can't fit everything into this workshop. But in this workshop, we implement variational autoencoder that uses only two basic layers. So two basic type of layers. The first one is the dense layer, or called fully connected. So this is a diagram of a basic deep neural network. So every neuron, so this circle is what we call a neuron, and there are these arrows. These arrows means that in order to compute this value, we have to multiply this value with the number of this the dash line. So this one multiply with something, you get some value, and then you do all the multiplication, you get like 4 different values, and then you sum that up together to get to compute this value. This is what we call dot product. So this is dense layer. So dense layer means is this one. This is one layer, and this is one layer, 2 layer, 3 layer, 4 layer. So there are 4 layers. So this one is input layer. This one is called hidden layer 1. Anything that is not input and output layer we call hidden layer. Okay, and the other popular layer is called convolutional layer. It is used a lot in image processing, and any neural network that do with image. So we can, if you want to, we can click on go to this GitHub to try to visualize, to look at what the convolution is trying to do. So the light, so this 4x4 grid is the image, and the dark blue 3x3 is our convolutional filter or convolutional kernel. So what it does is that it slides through the input. So for each of the 3x3 the input, so it perform this dot product that we have described earlier using this dense layer. You just multiply everything and then sum them up to create your output. Right, now we can scroll this one. We can go back to here. Alright, so this is the architecture diagram of autoencoder, which is the first neural network that we will create today. So as explained, so there will be input layer and output layer and there's some layer in between in every neural network. So this is an input and this is output. So in autoencoder, the input is an image. The output is actually the same image. So what are we trying to do with this architecture? Why do we want to create something to try to reproduce something from the input? Why don't we just copy and paste that? Oh, then we can get our perfect output, which is the exact copy of the input. The reason we do that is that to remove we want the network to learn the representation of your image. Say for example, if we look back at this apple image, so how would you describe it? We can say there's a red apple in the middle, there are some green leaves and branches in the background. right? Or we can just simply say it is a red apple. That's it. But computer does not see it this way. I mean the normal computer, not the AI type computer. So if you ask to computer to describe what is in this image, it will just read out, okay, this picture is green, this one is the different shade of green, the other picture is the green, etc, etc, etc. So you have to encode all the information. Maybe you have to save how many you have to save the like 1 megapixel, then you have to save one mega, the 1 million. You have to save 1 million values to only to describe one image. But we can just describe that as a human. We can just describe that in the one word. It's a red apple, right? 2 words. Okay. So there are a lot of redundancy information in this picture. Say there are 100. Say there are 1 million like parameters values that, but we don't really need that much to try to describe or these image. So that is why the AutoCAD is good at trying to remove many of these information that we do not need. So if we look at the shape, so these part they are is made out of two different small sub network, if you will. So one is called encoder, one is called decoder. The encoder will try to squeeze the information. So some high dimensional variable like 1 megapixel into something, a vector that is small in value, maybe just 10, okay, just 10 parameters or 100 parameters, that is able to capture the meaning of the input. So on this one, then after we have the inputs, so after we have learned the input, the job of the decoder is to restore that into an into a image with apple. So this is something that we can use an analogy that is like, okay, you tell, so this one is an artist, so it's a painter, okay, it's a painter. So you just tell the painter to draw an apple. Okay, that is the information you pass. You look at the picture yourself, and then you tell the painter, okay, paint a red apple. Then though this is a painter, and then the painter get your input with a red apple, it will then recreate a picture of a red apple. So this essentially is what it means. So we can see this in shape. So as we inside this encoder, there are different multiple layers. So as we move it towards along these the layers, we squeeze the information. So the what do you call the activation, so the output of each layer, it becomes smaller and smaller and smaller and smaller in size, and then we restore it. So and then in the decoder we do the opposite. We increase that layer a little bit by a little bit until it reach the full dimensional as the input. Okay, so now let's move on to this notebook. Okay, where is our notebook? Alright, let me shut this one. So how do we shut this one? We can use not here you go, manage session. Alright, terminate. Right. You basically you cannot create with this free version. You cannot have, I think you can have more than 2 notebook open at the same time. So let's just Google Colab and go to Google Colab and create another one. Okay. Right. Just use again. Auto encoder. Okay, so let me just comment out to save time. So I have added some code to make sure you install the correct TensorFlow version. But as I believe for this notebook, I believe it should work with the latest one. Let me try. No, sorry, before that, right, sorry, I think before that I will need to set the runtime. So we can change the runtime type. This is ignore this one. So this is the virtual environment I created. But you can use as Python 3. So hardware accelerator to set it to GPU. Right. So without GPU, it is very slow to train. So that's why we enable this GPU. Then we can, yes, then it will reconnect the kernel. Then we have to run everything again. Right. Never mind, I will just comment out just to be safe, to make sure the code runs without problem. So what I'll do is that I uninstall the TensorFlow. So I install the TensorFlow version, the GPU version, with this guy revision 2.3.1 to make sure it's compatible. Right, create Y for yes. Yes again. Okay. Okay, while we are doing this, actually it may be a good idea for me to start loading the next the next notebook that we will use, which is called VAE Faces. Right, do the same. Let's terminate this one. Runtime registration. Right, can't do it now. It's complaining about opening too many sessions. Okay. Okay, in this example, we use a simple example, so it's quicker to train. So it's MNIST dataset. MNIST dataset is image dataset, a grayscale of digit 0 to 9. So this one will just load the image from the datasets and make it into a data loader. So a brief introduction. So this one is TensorFlow uses tf.data as one of these data pipeline. So we can add this pre-process. We use a map. So pre-process is a function that we write ourselves, that you cast the image into floats, and then I just did a very simple normalization, is to divide it by 255. That means we normalize the value of the image into a 0 to 1, and then I can just add the chain by just calling this dot batch, and the batch size in the size I set as 256, so etc. Okay, I run this one. Alright, so this one is very fast to download, so we do not get the problem we have with the setup A. And okay, we'll just keep running it. So I will go through this fairly quickly. What I wanted to show you was the construct of the model. So for the encoder, as we can see, we will reduce the dimension from from high dimensional to low dimensional. So how we did that is we use a convolution layer. So this is the Keras API. We just call conv2d and pass in the number of filters. A kernel size, so kernel size is a 3x3 that we have seen. So by default we use mostly 3x3. Sometimes we use 5x5, but I think 3x3 is a default. And the strike 2. So strike 2 means that in this context means after this layer, the image size, the height and the width reduced by 2, mean by half. So if say for example, if the input was 28 by 28, after this layer when the strike is 2, then it become 14. Okay, then we add 1 layer, 2 layer, and then when this layer, so when the strike is 2 again, so 14 is half again to 7. So at the output of this layer, so originally it was 28 by 28, now it becomes 7 by 7. But on the other hand, the third dimension, the channel dimension increases. So in this case it is 1, but at the end here the channel dimension is become 8, so it is 7 by 8. So the last step is to flatten it, to convert this 3D tensor into 1D tensor, and then we apply a dense layer, which is a fully connected layer, to predict the Z dimension. So Z dimension is something we can define. That is the how many the size of the vector that we want to represent what the neural network has learned. So in this our example, what do we use? We use Z dimension 10. So it means that we are successful. So in this case, reduce the dimension of a 28 by 28 into only 10. So I think it's a factor of so this is roughly 900. So and we reduce it to 10. So that is a lot. So this is the encoder, and so as we can see, we can actually implement this very easily using Keras. We just copy and paste this. Just create that one to the copy and paste, and then change some parameters. And then on the decoder, so in the decoder, you have to take the output of this one of the encoder, and then you restore it to the full size of 28 by 28 by 1. So it is almost like a exact copy, a symmetric copy of this one. So the last one is dense layer, so you begin with the dense layer, and you reshape it, and then you also use a convolution filter followed by an upsampling 2D. So in here, when we go down the sizes, the activation map, this is what we call the 2D size, we call activation map. The activation map reduces in dimension. In this one, we do the reverse. We have to double the size, double the dimension, double the sizes. This is what we do. We call upsampling 2D by 2. So you just double it and then double it. And the final layer is to conv 2D. So at the end, the output will have the same shape as this one. All right. Okay. I probably have to speed it up a little. running out of time. Is already past one hour, and there we have a lot to cover. Okay. So after we create this encoder and decoder, all we need to do that is to connect them together. So the model input is the input of this encoder, and then we have to pass the encoder output into the input of decoder, and this one is our output of your model. And then we define a model to specify, okay, this is the input and this is the output. There we get our auto encoder. As you can see, it is fairly straightforward and easy, simple. Now we will run this one. and run this one, and run this. Alright. Alright. While it is training, we don't actually need to run 100 epoch. You don't have to run 100 epoch. Right. And so this one is to some boilerplate code to save the model. We have to monitor the validation loss. If it's the lowest, then we save the model. And this is early stopping. So if this guy validation loss has not increased for more than 5 epoch, then we will just stop it early. So although we specify that we want to run it for 100 epoch, so it may actually end well before that. Right. So okay, so let's not wait for it to finish. We will just look at these some of the result that I've used. I'll just stop it. We are running out of time. Alright, so this is what we get, the output. So the top row is the input. The output is the predicted value. So it shows that the autoencoder has learned the representation and then restore the result. And the only thing you will notice is that the output is a bit blurry. So this is one of the limitation of autoencoder, which will get fixed by using GAN. So what has the autoencoder actually learned? So in order to visualize it, so I changed the dimension in the Z dimension from 10 to 2, so we can plot it onto the graph, and then we can just rerun everything. And yeah, this is what we get. So on the right, we have this chart that encode the color of this digit, the digit from 0 to 9. So we can see that some digits are, so this one the same color, there's the same digit in this scatter in a group, scatter in this two-dimensional of z, the latent vector, the z latent vector, so one-dimensional, two-dimensional. So what we can see that some of the things that is not, something is good, that we can see that you tend to group some of the same digit in the same together, but they are not even. So for example, this patch, they are very densely packed together. This one is spread across a larger area, and there are many empty spaces that is not used. So we can actually improve that. So this is one drawback of this original autoencoder, and we can improve that using we make a tweak to that to improve that, and it is called a variational autoencoder. Alright, let's go back to our slide. Right, so this is the kind of the latent space that we get from autoencoder, but ideally what we want to get is actually something like this. So all the representations are grouped together, right? Spread uniformly, and there are some slight overlapping, but not too much. Here we can see there are a lot of overlapping. So in order to enforce that, we can use what we call a variational autoencoder, or we call VAE. The only modification is that in encoder, the autoencoder, we encode the input directly into a vector. In here, we don't directly encode into a vector. We encode that into a mean and variance of a Gaussian distribution. So in each of this block, you can say it is a Gaussian distribution, a 2D Gaussian distribution. So by enforcing that, we can make sure our latent space fall into the Gaussian blob like this. Okay, so this one basically encode into this Gaussian parameter, which is mean and variance, and then when we do the decode, we sample we sample from this Gaussian distribution that we have created. All right, let's go to this one. This is an interesting one. So just now we use auto encoder to create a simple image. Now we are going to use VAE to create faces and then to change to play with the faces. And then let's stop this one. Session terminate. Okay, let's see if I can time. Is this running? Yes, it is running. Right, let me, while it's loading, let me try to explain this VAE. We still have this guy encoder and decoder, like we still have encoder and we have decoder, but this time instead of a simple convolution layer, I created another block that is more not really complex. I just have to the only difference is that I add a batch norm layer, so it's com to the batch norm layer and leaky value. So leaky value is it is quite commonly used in generative more neural network to kind of like it encourage the, well, in layman term, it pass on more, no, in technical term, so it pass more of the gradient in back propagation, but in layman term I mean it makes the neural network easier to learn. Okay, so we have this down convolution, so essentially just a convolution 2D, and I add the batch norm followed by a leaky value. So it is similar in this guy on the other direction. So the convolution of the and decoder as replaced by this block also is essentially the same thing. We still have com2D, leaky value, and sampling 2D. The only thing new, the only thing new is that I added a more new Gaussian sampling layer, where you do the Gaussian sampling. You encode into this the mean and variance, and then from that you do the Gaussian sampling. Right, this is kind of like expected. All right. Let me check what is in the next slide. Oh, okay. After that, we'll go into like deepfake. Right. In Okay, in this example, I will use a pre-trained model. So in order to upload my model, I will need to do this. Let's say again, let me first create a new folder called models. Right. And in the GitHub, so the model is already in the GitHub. Now I will just try to upload it from the GitHub report. Right, chapter 2. Right, this model. Right. Oh, it's taking a bit longer than I expected, but okay. Okay, the loading of setup A is done now, but we don't actually need to use it, but just to make sure the code doesn't crash. All right, so we have created a VAE model. So in this one is that because when I develop the code, I use like multiple GPU. So this one is say if number device is more than one, then I call this one view will automatically make this model into a multi GPU model, so it train faster. Okay, so these are the new losses, so I'm not going to go through that. Blah, 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 blah. Right, let's just stop it. Let's not waste time. And I will now just load the pre-trained weight. Alright, let's try again. Yeah. Alright, let's hope this works. Well, actually, I think I might be just better to show you the result. Okay, let me check something. Right. Right. So, well, I think I'm okay because I forgot to upload something. Never mind. So if I just run this one, okay, there you go. So this is the output. So this is a input image. So this is what come up from this autoencoder. So it looks okay, but it's blurry. But as I mentioned, this is the limitation of this autoencoder. So the subsequent cells are more technical. So if we want to learn more about that, we can. You feel free to explore this one. And there is actually a cool one. I'm not sure you can run it now. I can just show you this example. So you can learn this variable, latent variable you have learned. Then you can play with that to basically slide through this variable to create the image. So for example, if I have something like this, I can just increase the eyeglassless in the latent variable. So to generate, you see there's eyeglasses here, and say in this case, more chubby, etc. And at the end of this one, there's actually an interactive slide bar that you can use to actually upload your photos and then to create for the autoencoder to learn that, and then you can slide the bar and then to change it. All right, so sorry, but I think I have to end this slide correctly. So you will feel free to follow the instruction in the GitHub repo to try to play it. Now we have 15 minutes left, so I'm sorry, have to quickly go through the next slide, which is the deepfake one. Very quickly, so deepfake is although there are different techniques to do a deepfake. So the one that we will concern about is in the bottom. It's basically do a face swapping. You swap the face. This one is the different. This one is that you have a driving video. So someone is talking. So you basically transfer the motion of this into this image. Then you drive this image. So the result will be that there will be a talking video talking with these woman faces. Okay, so this one drive this one, the still image. But on the other hand, so deepfake, we do a face swaps. So we swap the face of this Chinese leader into this guy Barack Obama face to become like this. We can see that the face shape, we have squeezed the face shape to the face shape to fit into the small head of Barack Obama. So it is actually, deepfake is not a single model. Many people have misunderstood. It think it's a single model that does everything magically, but in fact it is made up of many pipeline. So there are many different pipeline that we use. So in each of the stage, there can be a neural network model to do that. The deepfake part, the autoencoder part, is only this tiny bit. I will go through each of the steps. So the first one is that we try to detect the face, and then we detect the landmark. So landmark is basically this different key point around eyebrows, noses, mouth, lips, etc. eyes. Then we do a face alignment. We try to, if we have these we try to align the straight into the center of the image and in a vertical way. So, and then this step we crop the face, and then we do the face swap. We use the autoencoder to transform this face into this face, and then with the new face we copy and paste into this one. All right, but when we just copy and paste blindly, so it can have create some artifacts. Maybe the face is bigger than this one, so we have to create a mask to do what we call a shape refinement. Then eventually, so this is the result of this face swapping. Right, this is just to show you an example, the more zoom in version of what I mean by face alignment. So the pipeline will detect your face and then the key point, and then we have a reference key point of your face. Then we try to, when we work out the rotation matrix that used, then we apply to the image to kind of rotate the image. So we can see now this face on the right is more straight, not tilted. So we have to have both images also to be similar pose. That means so that we can do this face transfer easily. All right. So now we talk about the autoencoder part. So the autoencoder, as we have learned, is to learn the representation of the of your face, of your image of your face in this case. So we have in this deepfake autoencoder, we have a target face A and face B. So these are two faces that we want to swap. So we use the shared encoder to try to learn the latent means the hidden representation of the face. Maybe it can be whether you're smiling or not, whether you the head pose, your eyes open or closed. And then we train a separate decoder for each of the face A and B. All right. So in each of these like pipeline is just basically just one autoencoder. This is another autoencoder, but they share the same encoder. So after that, so how do we do the phase swapping? We use this encoder to encode phase A into some latent phase A. Then we take the B, the decoder B. So we use this one, we learn about the phase pose, eyes open or not, and then we apply the decoder B style. It is like so the decoder B learn that, so this is going to be a woman with long hair, etc. And then we use this decoder B to restore the what we have learned from the phase A. Right, so this is essentially what happens. So the model wise, it is very similar with what they have seen in the auto encoder for MNIST, despite it is it can be like bigger, slightly bigger, but the concept is the same. Right, so this is just to illustrate when we paste the face back, we have to create a mask using different techniques so that it falls inside into the new face, so it's not like outside of it. Right, so this is a code. There is a notebook that you can run. It is also in the GitHub repo, but we don't have time to run it now. But you are feel free to check it out. So I provided, I uploaded some code that use Nicholas, that had contained Nicholas Cage face and these Barack Obama, no, Donald Trump faces. It is actually the database uploaded by the original Deepfake creator. Alright, so the GitHub report actually doesn't it show you all the entire pipeline, but the result is actually not that great because it is a simple model. So if you were really interested in generating deepfake, a good quality one, there are some GitHub report that you can try yourself. Right, so we have a few minutes left, so I'll quickly go introduce about the again. So this is the diagram. If you kind of like move this part into here, so this is our autoencoder. So but it's called differently. So it's called generator and discriminator instead of like and decoder and encoder. So I won't go into the details of how it works because it is a lot of details. But the general idea is that why just now we mentioned that autoencoder can create a blurry image because it uses L1 loss. L1 loss means that if you move your head, say by a little bit, so you are not totally aligned with the original. So but to human eye, it is still the same face. But to the computer, when you use L1 loss, it can create a huge, a large error. So L1 loss is not actually a good metric for generative to generate image. The better way is actually to, instead of defining a loss function, we create a neural network and let it learn its own custom metrics. So this is what this discriminator is for. It's a neural network. So it just look at the image that you generate and then it will judge whether it is a good or not real image or is a fake image. So this one is our loss function. It's a kind of an evaluator if our custom loss function. So this one, because of this one, we make a lot of improvement is the image quality. Alright, so here are some important GAN models if you are interested in like learning more. So these are some of the important ones. If you are interested, so you can, I have written a blog post about it. You can just go to this link and to read the details. So I've also included two links that you can actually click and then try it yourself. So you can just drag and drop. No, not drag and drop. Do some sketches, and this one also do some sketches. Then it will generate realistic images for you. Okay. Alright. So as I mentioned, currently the state of the art is Dialgan. So there are many different variants. There are style gun V2, but really is a style gun that is set the become the de facto like network architecture in generating faces. So we can improve the deepfake by substituting the autoencoder with style gun. Some people have already done that, and you can quite easy Google it to see to find the GitHub repo to do it. And so all these the models here are included in the book, in my book. So if you wanted to know the details on how to create them, feel free to check out the book. Except for this one, because this was published after my book, so this will come up after my publish my book. So it's Appen AI DAO-E for text to image generation. So it is the result is also very impressive, where you can like type in some words, like create a avocado shape chair, that it will just generate these like different kind of like chair with avocado shape and color. So it is also quite good to look at. And at the end, so we will not have any Q&A session because of this like time constraint. So feel free to connect with me on LinkedIn. You can just say okay, you attended my workshop, to connect with me, then I will accept the connection. If you have any question, feel free to ask me. Okay. I have also a blog post, but that you can follow me. Okay. Finally, thank you for joining. It is a good experience for me. I hope you enjoy my talk, and hopefully you have learned something, a little bit things today. Okay. So thank you very much. Welcome and see you. Bye.